We're going to get bonus points? We're going to get bonus points?
Bonus point for today?
No, we here. We only 4 people.
Yes. Give me that. Too greedy.
I should have got it earlier. I came like 2 minutes early.
1, 2, 3.
It's cold outside. Well, it's not super cold. It's a little chilly. Rain's cold. 64 last night. First 59, right? That is a little rain.
Okay. Good morning. Last time we discussed Laplace transform. You want a quiz?
On the formula?
Laplace transform.
On the formula?
Alright.
No.
Let's try one. E to the at, negative at, ut, we have, what's this? Last time I said memorize this. What is it? No one? I should take the bonus point back. Alright, that one is 1s plus a. Right. And the region of convergence is this one larger than negative a. Right. Some special case, if e to negative t ut, that gives us, what is this? I used to know.
1 over s plus 1.
Right? 1 over s plus 1. And this s, is a sigma equals this, right? And greater than negative 1. Right? How about this one? xt equals ut. What is a? What is a here? 0. So that one equals you mentioned a equals 0. 1 over s. Right? And sigma is greater than 0. Right? Questions on this? It's good, right? Today we are going to discuss properties of a Laplace transform. Right. The first one is linearity. Laplace transform is linear. We already know the concept of linear. Anyone can guess what is the linearity of Laplace transform? For example, if for x we have this, and if yt we have this, what is the linearity of a Laplace transform? If we have a constant a times xt, then plus another constant b times yt, and what is the Laplace transform of this? That is a linear combination of this and this, right? And constant a. What is Laplace transform of this? Can you guess? Here, Laplace transform is linear. What does that mean? A, this, right? Then plus b times this one. Right? So if x, sigma x, the Laplace transform equals this, and yt, the Laplace transform equals ys, then multiply by some constant, then add all this together, the Laplace transform of it is the same linear combination, A, B, plus, the same linear combination of the Laplace transforms. Right, now we have an example. E to the 2t plus e to the negative 3t and ut. What is this? Let me put another one. So this is 4 here. Okay. What is the Laplace transform of this signal? Anyone can tell us? This input signal has 2 signals, right? The first one is e to the 2t ut. Second one is 4 e to the negative 3t ut. Use the linear property. The Laplace transform of this signal is the Laplace transform of this signal, then plus the Laplace transform of this signal. Okay, now what's the Laplace transform of this signal?
Whatever s minus 2.
What's the first part? 1 over plus 2, minus 2?
Minus 2.
Minus 2, okay. So 1 over s minus 2. So that's the first part. It's good, right? Very simple. All right, what's the second one? Linear property. Hello? What's the second one? 4, okay? 4. Because that's b equals 4, right? 4 over s plus 3. As easy as this. Any question? Do we forget something? Huh? ut. This one e to the 2t times ut. E to the ut. Together give us this. Okay? Right? Do you forget something? The region of convergence. What's the region of convergence for this? The real s, the real part. Well, that is the real s. Alright. So, this is the real s. This one is the real, or sigma. So the sigma will be greater than for 2. And this one, sigma greater than negative 3. If I draw this, the first part is 2 here, to the right. The second one is negative 3, okay, to the right. So what is the overall region of convergence? These two must be satisfied at the same time. So the overall will be this one, right? So the region of convergence for this will be sigma greater than. We take the overlap of the two region of convergence. Questions on that? We are going to use these properties a lot of times. You need to memorize this. Okay, the second one is time shifting. That means we shift the input signal by some time. For example, xt minus t sub 0 and ut minus sub 0, this. Actually, I don't need this. Right? So xt give us capital X. So this one shifted by some time. What is this? This one will give us the original one, but multiply by e to the negative t sub 0 f. Let's give you an example. What is the Laplace transform to this signal? What's Laplace transform to this one? Right? We know this one is a shift by 2 seconds of the ut. Right? So the x is ut. Shifted by 2 seconds. And that one will be equal to the original Laplace transform, then times e to the negative t0 times s. So what is it? Let me ask somebody. Austin Gibson. What's this? You are late. Okay, so Gillian Thomas. Gillian Thomas? Still? Okay. Corey. What is it? Can you try?
XS would be e to negative 2s.
First one, delay. First one we consider the original signal, which is ut, right?
The ut minus 2.
So the Laplace transform of ut is what? 1 over s, right? So I copy this. Make sense? Everybody?
Yeah.
Alright. Then times e to the, what is t sub 0? 2. Why is 2? It's here, right? And 2f. That's it. Everybody can do this?
So that's the proof which is negative.
Pardon?
That proof which is negative.
This one is time shifting. Linear is here. Right? We are going to use these properties a lot of times. Right? Better know this. Okay, let me move. It's good? Alright, the next one is time scaling. Time scaling means x alpha t. See, we multiply by t, multiply alpha to t. And this one will be equal to, give us 1 over alpha and x s over alpha. All these properties can be proved, but we don't do that. We only need to know how to use this. If you know x t give us a capital X, and then if you multiply by alpha to the t, then the Laplace transform is you replace the original s with s over alpha in the Laplace transform, then divided by alpha.
What is that that's multiplied by t?
This one?
Yeah.
Alpha. Right? Just a constant. You can use a, you can use anything. Right? Just a constant. Any question on this? All right, now we have an example here. E to the negative t ut. What is this? What's this? It's on the top.
1 over x plus 1.
1 over s plus 1. Eh? Now we are going to use this, try this time scaling. So e to the negative at, see, I multiply with x t by a. And this t also need to multiply by a. But ut, what's the difference? No difference, right? Same thing. Right? So I still write u at, but a doesn't matter, right? A is constant, right? Like this. What is this? Oh, we already know that it's on the top, right? But I want to use a time scaling property to get this. What is this? More active participation, right? Can you tell me? What's this?
What is what?
What's the Laplace transform of this one? Don't look at the top. We know that is equal to this, right? I want you to utilize time scaling property to this one to get one, to prove that that is correct. Right? I tell you the Laplace transform of this equals this. We know this. What I want is this one multiplied by a, this one multiplied by a, but we said this one multiplied by a is the same thing, right? So I just don't write that a. Then what is the Laplace transform of this function? Use this property here.
So it's going to be 1 over negative
1 over
negative a.
Okay, we look like this. We know this function is derived from this function, right? How to get this? Multiply by t with a constant a. So that is exactly this property here. So the Laplace transform of this function, which is this function, right, is the original Laplace transform, but the s, the original is this one. But now the s is replaced with the s over a, then divided by a. That is the Laplace transform. Right? So what we have is here is the original Laplace transform, which is here, so s plus 1. but that is not S. That is S over A here, right? So this one actually is over A here. Make sense?
But you don't have to write the A.
Huh?
Do we have to write the A?
What do you mean?
Do we have to write the A?
Yeah, because there's A here. So
No, in the answer.
you mean this A?
No, in the answer.
In the answer, yes, the A is given.
Okay.
This is a constant. Right? So if we don't have this A here, this one is 1 S plus 1 here. Right? But we are going to replace this S with S over A here. So that will be equals this. Is that enough? No, we still need divided by A here. Right? Right? So then we divide by A here. Right. This is the Laplace transform of this one by this property. Any question on that? Oh, you mean right? Oh, we said that one is here. Is this the same thing? Is this one equals this? Right? We simplify. This one equals A multiplied by here. Okay, S plus A. Yes, that is it. Any questions on this? It's good? Everybody? I will give you a quiz right after this. Right? Questions on this? Questions asked. You don't expect after the class to understand this. You understand this right now. Okay, let me repeat. The Laplace, suppose the time shifting property is, if first one you know a function, time domain function, suppose we know its Laplace transform is this one. No question on it, right? Give you time domain signal. You calculate this, or I tell you, no matter what, we know the Laplace transform is this. Then my question is, how about this signal multiplied by A with this t? What's the Laplace transform of this? Well, you don't need to calculate from the concept. We can get the Laplace transform of this directly from here. You take the same form of this, still x, no matter what function this is, you use the same form. But this S is no longer S, must be replaced by S over A. That's the first step. You take the same form of here, but replace S with S over A. Then we multiply by a constant 1 over A. That's it. That is the Laplace transform of this. So you don't need to calculate it, you just use this property to get it. Does it make sense? Everybody get this? Okay, now let me give you a quiz. Suppose I have a function xt, the Laplace transform is, let me make up some number, equals sine 3s. This one is this one. Laplace transform this. Okay, that times 4. Try to confuse you a little bit more. Then what is this one? 2t. What is this? What is the Laplace transform of this guy? Okay, first one we know. This one is called time scaling, right? The only difference between this and this is we only multiply the time by 2. That's all. The form does not change. Make sense? Right? So we can get the Laplace transform of this from here by some manipulation. That manipulation is we keep the function of this one. So we still use capital X. Capital X in this case is what is it? for sine
3s divided
3s. Okay, that is the original, right? But we need to replace that s with
s over 2.
s over 2. Okay, now that's it.
And then divided 4.
Then divided by 2 on the top, on the front. That's it. So that one will be equal to 2 sine 1.5s. Questions? Good? Show me, give me some signal. It's good. Next class, we are going to use a lot of examples, okay, to test you with all these properties. Because Laplace transform is very important. Usually, you should do this by yourself. But I will spend one lecture next time. We do together. And because if you are EET in 412, you need to do this. If you are in later time, take 477, 478, 477, I don't know that, 478, no, 477, you need to use a lot of this. Laplace transform, inverse Laplace transform. Okay, good?
There's some
Alcohol. Okay, are you good here? Okay, next property is called which one I can use? This one is better. Alright, next property is called multiplication by a power of t. What does that mean? Again, we know x, little x, give us a capital X. So t to the n, xt. What's the Laplace transform for this one? We already know the Laplace transform for this. Then we just multiply by t. What is this? This one will be equals we know this, right? We take the differentiation of this with respect to s for n times. Then multiply by -1 to the power of n. Everybody good on this? Before I do example, I let you try first. And let's. Again, what is ut? Give us. What's the Laplace transform of ut?
1 over s.
1 over s. Perfect. That is what I want. Now, what is the Laplace transform of rt? Is this property? What is rt?
It's ut
Times what?
an impulse.
Times t?
Yeah, T times U.
T times ut, right? We have done a lot of homework for this one. T times ut equals RT, yeah, right? T times ut equals RT. So that means what is n? 1. What is xt?
UT.
ut, right? So now tell me what is this? That means we need to take the Laplace transform of ut. How many times? Differentiation with respect to t, how many times? 1 time. Right? So that one will be d ds. Luckily only 1 time. And 1 over s, that is the Laplace transform of ut. Then that's it. Times
Negative 1 to the 1.
negative 1 to the 1, which is
Negative 1.
negative 1. That's it, right? So that's negative sign. Okay? Can you do this? If you don't know how to do this, go back to 168. Differentiation, right? That's not our topic to do this, right? What is it? 1 over f, take differentiation, equals what? Is this one equals, okay, first one is negative sign, don't forget this, right? And this one is s to negative 1, right? Alright, so is that one equals negative 1 to the s negative 2? Yes, right? Right? So what is it? Is this good? Yes or no? Yes? Yeah, that is good. If you look at the table, that is. Further questions on this? It's good? Alright, then we'll go next one. Next one is multiplication by a complex exponential. That means, again, xt, we know the Laplace transform of this. We multiply by e to the at. What is this? This one is, okay, again, the original Laplace transform. But replace this s with f minus a. So easy. You don't need to calculate the Laplace transform of this directly. You know this, right? Just copy everything here, but change all the s into f minus a. Let's verify before a real example. What is UT? One over x. What is e to the negative at ut? That is the first Laplace transform we have done in this chapter, right? What is the Laplace transform for this? Still remember?
Yeah.
Over there, right? Okay. 1 over s plus 8. Are you sure this is correct? Don't look at that. I know that is correct, but look at this and look at this. Is this good? Use this property. And we know ut equals 1 over s, give us 1 over s, right? Now this one multiplied by e to the negative at. So this negative a here is the a here, right? And that means we need to replace this s with s plus a, right? Right? So s with s plus a. It's good. Any question? You need to memorize all these properties. Let's try another one. Suppose cosine omega t times ut, right? This one give us s over s squared plus omega s. Suppose this is correct. Then I multiply e to the 3t cosine omega t times ut. What is this? Anyone can do this?
The top of
What is on the top?
S plus 3,
Perfect. S on plus 3 on the top.
and S squared plus omega squared plus 3.
S squared plus omega squared plus 3. Any questions on this? Everybody agree? Can you see how to get this? No? Everybody? Who can get this? Raise your hand. Who can get this?
How do you get the bottom like that?
Huh? The bottom has a problem. The top is good, right? The bottom. Any question on the bottom?
Would the bottom be plus 9?
Plus 9 here.
Yeah, because S is squared.
The key here is we keep all the form, but replace s with s minus a. In this example, replace s with s plus 3. Question on that?
So S plus 3 squared.
S plus 3 squared. So this 3 should be here, not here. Now you see it? Good? replace s. Every s is replaced by s plus 3. Not anywhere else. Right? Not hard, right? Everybody got this? Okay. Let me. What's the first property? Linear. What's the second one? Time shift. Time shift. Time delay. Time advance. Okay, time shift. What's the third one? What's that?
Time scale.
Time scaling. Multiply by the t by some constant, right? What's the next one? Fourth one? Multiply by a power of t, right? Times t or times t squared times t. No. What's the fifth one? Multiply by a complex exponential. Okay, so this one will be the 6, right? The 6 will be a differentiation. Differentiation again. So d dt xt. What's this? We know xt gives us a capital X. Right? So we take the differentiation. This one is again we have this, right? But we need to multiply by f in the front. Most probably, that's it. Do you know why we want to use this transform analysis? We bother transform a time domain signal xt into a Laplace transform, then do something, then use the inverse Laplace transform back to the time domain. Why we bother all this thing transform to, transform back? Now look at this. If we ever have a differentiation in time, we don't like that, right? Do you like solve differential equations? No, you don't, right? Differentiation in frequency domain, that's easy, just multiplication. Right? Differentiation in time, just multiply by this one here. Right? So that is one reason to do this. But sometimes we have initial condition. That means this signal is not initially, we have some initial conditions. Right? So in that case, we are going to -0. X, this is a small x. Right? That is, this one is a small, this is a big X. That is the initial value when t equal to 0, the time domain. Good? Alright, now let's example here. What is Laplace transform of RT? Hi, I didn't write here, okay? What is Laplace transform of RT? 1 over f squared, perfect. Okay, what is ut? We know ut equals what, alright? Okay, now don't think about that. Don't look at this, don't think about that. We know this, and use this property to get this. So we need to find out how to get ut from RT. How are these two related? differentiation. Differentiation of RT with respect to t give us UT, right? That is this one. So what is the Laplace transform of UT? It is this one, right? So I just copy this, copy this. What next? Multiply by S, right? And minus the initial condition. The initial condition when this one equals t equals to 0, what is it? Still know the real form. 0, okay? Minus 0, okay, we don't care. So what is this? Is this true? Yeah, huh? Somewhere here. So we take differentiation, then we just multiply. We take differentiation in time, we just multiply S in frequency or in Laplace term. Any questions on it? Looks like no question, but the question is we need to memorize this, right? Later time we are going to use this, all this property to solve, to do a lot of Laplace transforms. So you need to memorize all this. Oh, this is the number 6. What's number 7? Integration. Yes, you are here. We finish the differentiation, the next one will obviously integration, right? Right? X tau d tau. Right? May I ask why I write x tau d tau? Why I do not write xt dt? Integration. Is this supposed to be xt dt? Why I write x tau d tau?
Because you have time, the interval.
Okay, the time will be here, right? To avoid the confusion. You can write t, doesn't matter, right? But you need to keep in mind, this t, these two t are the same, but it's different than this t. So you need to do this first, then you replace that t with this t. Confusion. So that's why in the slide, I use the lambda, the lambda, okay? That doesn't matter, just the integral variable. What is this? I want somebody to guess this. Educated guess. Differentiation. In differentiation, what this one? If the initial condition equal to 0,
S
times S, right? That is for differentiation. Now for integration, what do you think? Oh, you have that. Keep quiet. Right? What is it? Divided. Perfect. Differentiation, the integration is divided by S. And we don't even need to consider the initial condition. This is even easier than the differentiation. We can still use that UT-RT example, right? How are UT and RT related? RT is the integration for UT, right? So RT, we know UT give us 1 over S, right? And RT is the integration of this. So that means this one will give us copy this, then divided by S, right? That's it.
Would have been a negative?
No, no negative. Only, see, only divide by S, no negative. Any questions on this? Right, now we have a more serious example. last time we mentioned cosine omega t, ut, we ignored ut, give us s squared plus omega squared, and on top there's s on top, right? Now, how about this one? Sin omega t. Given this, and what is this? Use this property. How to obtain this signal from here? How to get this from here?
Would be 1 over s squared plus
One, you directly calculate the result. What is it?
1 over s squared plus omega squared.
How did you get this?
You multiply it by 1 over s.
Multiply by 1 or s. So that means you said this one is the integral of this, all right? So you divide by s, that means this one is the integration of this one. That is the question I'm asking. How to get this from here? And he mentioned that, okay, just this one integration, you get this. So that's why this one, you just divide by s, get this one. That is his reason. Right? 90% is correct. But there's a little detail need to be corrected. You try to represent this with the integral of this one, it's in the right direction. Okay, yes, it is kind of integration of this, but not exactly like it. How to get this from here? Cosine omega t integration with respect to t. What do we have this? Let's give us a sine omega t, right? Do we have something here?
I was going to say there's a negative.
Negative?
Yeah, negative.
Not negative. Because this differentiation equals cosine, so that's positive.
See the egg, if you remember?
What?
The eggs, all of the eggs.
What is on here? 1 over omega. Okay, perfect. 1 over omega. Because when we take the differentiation of this one, sin omega t, that equals cosine omega t, then times omega, right? Then omega cancel, so that gives us this. So this one is the integration of this, then divided by omega. Right? So this one here will be equals this. Not 1, it's multiplied by omega. Does it make sense? Not quite? Right? Cosine omega t integration equals 1 over omega sin omega t. That is in math 168. Yes? What we are looking for is sin omega t. So you need, this one is the integration. The integration gives us this one, right? But that one is this, not this one. This one is we need to have multiplied by omega at the front also. So this part gives us this one. Because we do the integration here, we get this. So this one divided by s, we get this one. That's perfect. So this one, integration, we get like here. This one. Does that make sense? Cosine omega t integration equals this. Not equals sin omega t, equals 1 over omega times sin omega t. So that's why this one divided by s equals this one. So that is correct. But what we are looking for is, we don't have this one here. We only have a sin function here. So we need to multiply by omega on both sides. So we get this. Good? Look at this, you can discuss. So any questions? Any question on it? Next class, we are going to use real examples to solve this, but I will let you do first. So that is a quiz. I'll give you all the Laplace transforms. So now we know how to calculate Laplace transforms. I'll give you some, either I'll give you some difficult ones, or you can calculate like this one. It's very simple, you know that. Then you need to utilize all these properties, 7 properties we discussed so far, and try to find the Laplace transform for complex or complicated signals. It's linear, multiplied by some exponentials, multiplied by some powers of t, time shifting, differentiation, integration, and all this. We have another, right? Everything's good here, right? That is how many? 7, 4, 5, 6. Okay, so next one is 8. We discuss all these operations. What operation we know in this class? I said that is a new operation we introduced in this class. You may not know this before, and this is important. You learn plus, minus in elementary school. You know all this, okay? Then what we learned in this class? Convolution. Okay, so now we need to discuss convolution. If xt give us this one here, and if yt give us capital Y, this, then how about if the convolution of x is the y? That is the real reason we discuss transform analysis. We know this one is not easy to calculate, right? You forget, right? In the midterm, we have done this time domain convolution. Is it easy?
No.
No, okay, definitely not. Right? So that's why I'll give you this, I'll give you this. I ask you what the convolution is. What you do is, before you need to follow our procedures to do that, no matter how hard it is. Now we have a new trick. Instead of do convolution directly, you calculate the Laplace transform for this, you calculate the Laplace transform for this, you get this. Then, for this, the Laplace transform is multiplied together. You can do this, right? Multiply two polynomials, that's easy. Then you go inverse Laplace transform, you get this convolution. So that gives us a new technique. That is called transform analysis. Give you time domain signals, you not easy to calculate, no matter what, not easy to manipulate. What we do is we take the Laplace transform, we take Laplace transform, we take Laplace transform. Then in Laplace domain, all this convolution is just multiplication. Differentiation is just multiplied by s. Integration is only divided by s. All these things are much easier than in time domain. Then once you calculate this, you take inverse Laplace transform, we get what we want. So that is the purpose for all this Laplace transform, inverse Laplace transform, which will be discussed later. It's called transform analysis. In EG 412, and we all manipulate with this one. Analyze the circuit in Laplace domain. Okay? Any questions on this? Alright, next one, we are going to list all typical Laplace pairs. Called Laplace transform pairs. What is UT? 1 over S. What is delta T? How we get this from here? We will do this, at the very beginning. How we get this from here?
Either integration or difference.
Okay, differentiation, right? This one integral get this. This one differentiation get this. So this one is differentiation. This. Then what is this? Differentiation means multiply by s or divided by s.
Divided by.
Multiply. So that's 1 equals 1. Multiply by s. So this one multiply by s equals 1. Is this one reasonable? Right, let's discuss some physical meaning of this one. You may think, this one, you don't like this, right? Actually, this one has very, this one is very beautiful. Look at this signal. This is in time domain. This is impulse. Means the width is very narrow. F equals 0. The amplitude equals infinity. This one is the Laplace domain. At the beginning, we said it's related to the Fourier transform, so it's in frequency domain, right? So what does that mean? The Laplace transform of this impulse equals 1. We know the Laplace transform must be a function of s. So this one is also a function of s, or in other words, function of omega, frequency. So this one is a function of frequency. So this one is a function of frequency. Where is the frequency?
0.
Right? So this function is a function of x, right? Is this one is a function of x? Yes, right? Where is the x? What is x? Okay, no matter what the x is, it's always equals 1. If you draw this, okay, x, this is x, okay, so no matter what, it's just like this. The x can be anything here. Make sense? The x can be anything. So that means this frequency can be anything, and the frequency component is always 1. I want to repeat this in your head. For any frequency, the amplitude equals 1. What does that mean? So what's the bandwidth for this one? Infinity. Any frequency. Frequency can be equal to 1 million, can be equal to any frequency. And all the amplitude equals 1. So this is ultra wideband signal. The bandwidth equals infinity. And we cannot implement this in time. Why? Because you need infinite bandwidth. No one has infinite bandwidth. So this one is like this. You cannot implement this in time. Because you need infinite bandwidth. Alright, so this one equals this. Alright. What is this? That is called time delay. And it will be equal to this one times exponential, right? That exponential is e to the negative t sub 0 times x. Then multiply by this one, so the 1 is gone. And we don't need to write it down. Question on this? Alright, next one. RT. What is this? Over s squared. What is t? T to the n ut. That is multiplied by a power of t. How to deal with that? The differentiation with respect as n times, then times negative 1 to the power of n. Right? And we know ut is this, so the result will be equals to n is s n plus 1. What is n? This one. What we call it?
Factorial.
Factorial. Means n times n minus 1 times n minus 2 all the way to 1, right? This one equals this. We just apply the differentiation for capital N times to this one, then multiply by negative 1 to the power of n, we get this. Okay? ut minus t sub 0. What's this? This one is this one, 1 over f times delay, right? Delay is here, so e to the negative t. Right? I'll make this one make you happy. What is this? One over s plus a. That is the first Laplace transform we ever discussed. We analyze system usually is called harmonic system. Means the input, output all are cosine or sine functions. Right? So far we discussed the circuit analysis. Everything is transient or called harmonic system. So we deal with a lot of cosine functions. So we are going to, this one we need to pay special attention to cosine function. So cosine function times ut means we only start from 0 to the right. What is this? We already mentioned here. Right? This one will equal to f squared plus omega squared, and that one will be an s on the top. And the next one will be sine omega t and ut. What is this? This one will be s squared plus omega squared and omega on the top. How to memorize these two?
The sign works just
You memorize these two together, right? First one, both have the same bottom, so s squared plus omega squared. So that's easy. You need to memorize this, right? Right. My trick is for s, I don't have s on the top. If this cosine no s here, then I need to put s on the top. That's my trick. You know that one is s, another one is omega. Right? But it's easy to forget which one is which. So maybe this one is omega, this one is s. So if there's s already here, then there will be no s on the top. If there's no s here, then that's my way to memorize this. And those are, I said, very useful for harmonic analysis. Then sometimes the input is not just cosine function, right? So instead they are attenuated cosine function. So like this, negative e to negative at times cosine omega t times ut. We have exponentially decreasing function multiplied to cosine. So what is this? Now we need to record the property. This is, we know this, right? This one equals this. So multiply by exponential, complex exponential. We keep the same form of a Laplace transform, but we need to replace that s with f plus a. Right? So this one will be equal to, we keep the same form, but we replace f with f plus a. What is on top? S plus a. What is on the bottom?
S plus a squared.
Okay, s plus a squared, then plus omega squared. Omega is the angular frequency. Right? What is this? Negative a times sine omega t times ut. What is this? On the bottom, still the same thing, right? S squared plus omega. But in this case, we need to s plus a squared plus omega squared. What is on the top? Omega. We don't have s, so we don't need to replace anything, just omega. That's it. That is all Laplace transform properties we need to know so far. And I suggest you need to memorize all of this. At least like, we have a lot of more properties. I didn't list it here. The reason is we do not use them a lot. So So it's not necessary for you to memorize this. But all these are very typical, very popular. If you can memorize this, then later time, when you do the exercise, you are going to very fast. And you won't get frustrated, oh, what is this? What's the Laplace transform of this? Because, okay, you know there's a property multiplied by e to the negative at. Then it's very simple to do. I'll give you a few minutes to review all this, try to memorize this. Right? And if you have more questions, we can discuss. We only discussed the 3 slides in the lecture note. So page 69, 70, and 71. In the slide, we do not have so many examples, but here on the board, we use we give you at least one example for each property.
this right here is just.
This one will be the same as this now. The same function there.
That was then everywhere else.
Anyone else need to sign?
Substitute in.
So I'd like starting off select through my outlaw this morning. That's why I wasn't at 316.
That's your homework?
Yeah, reason for it. So
So
maybe
homework is this. So you skip your 316. You're not in 316 because you are doing the homework of this.
I like woke up at 8
Okay.
and it takes me like an hour and 20 minutes.
Okay. So you did this last night.
Yeah, I did this last night.
So that's why you skipped 316. You know what I'm talking about, right?
Yeah.
If you want to pass this, you want to fill 316. Right?
No, this is homework for me.
Oh, this one 316.
Yeah.
Oh, and you should do homework early. Right? So attendance is 10%, the homework is 10. Oh, yeah, you smart.
Okay, so
So that's why you skip class. The class is only 10%. It's only 10%.
well, Savannah would be in turn for homework again, so I have her homework as well.
Yeah, she wasn't here.
Yeah. I was supposed to.
Okay. Okay. Who needs to sign this? Homework is important. Class is more important. Right? You do not, you can ask them. If you don't do class, it looks like you cannot do the homework. Or you spend more time, more effort. Okay, any questions about this?
Been watching the YouTube video, man.
Everybody knows what we are going to do next time. What we are going to do next time? The examples. Who do the examples?
We are.
Yes, you are going to do the examples. And that will give you bonus point. That means what are you going to use?
The is. Something about it is.
Read the lecture notes. Right? So any more questions about what we discussed so far? All the properties. I think the only question is the problem is you need to memorize. You need to put everything in your head, right?
The name.
But so.
They like to